Hello guys, how are you? Once again, this is Hans Awia. In this lesson, we are going to look at understanding vertical motion. We are going to interpret and plot free fall motion, and we'll also look at objects falling in fluids, that is air and liquids. Okay, before we go on and explain things, let's go and look at a simulation on vertical motion. Well, here is our simulation. The object will be fired from here vertically upwards. What we need to note here is the movement of the object, particularly its speed as it leaves here from the point of release to the point where it now returns back. That's the most crucial thing. So we are now firing the object. I've set it to move slowly. Okay, watch closely. Here it is, it's moving faster. It's a little bit slow when it gets here, then it comes back following the same path. It's following the same path. Let me fire it up again, and I want you now to concentrate on the speed here, the speed of the object. Concentrate on its speed here at this point, right? Just before turning back. I want you to observe and tell me what you see. Yes. What can you say? What can you say? What can you say? Now look at the speed of the object here. Just after being released. Just after being released, and compared to the speed towards the end, towards the highest point in this direction, the upward direction. I think by careful observation, we can tell that the speed on its way up, the speed is high here. The speed is high here, and the speed is much slow here. It's much lower at this point. So the object is moving slowly until it actually stops. It stops at some point here. It stops at some point here before returning back. And as it now moves in the opposite direction, like coming down, its speed will be much lower, but it keeps increasing until it reaches the maximum speed when it's now here, right? Let me do it again. You see, slowly coming back, gaining speed, moving faster until it reaches this point. So now this is how we explain what we just observed. When we throw something upwards, it eventually comes back to the surface of the earth. An example, if you jump high up, we also end up coming back to the ground. If we jump right up, we end up coming to the ground. You can't just go up forever, right? Or maybe stop mid-air. No, it's not possible. Okay, what are we saying? This proves that indeed there is a pulling force that is responsible for pulling things towards the center of the earth. This force is called the gravitational force. We also know that jumping from a height of 1 meter is much safer than jumping from a 10-meter high tree. Yes, I don't want you to get in trouble because this is dangerous. You can't try it, but here is something that you can try. You can take an object of the same object, right? Same object, just same object, and then maybe a small, even a pen, and hold it 30 centimeters above your hand. Having placed your hand on the table, 30 centimeter high pen, then you drop it, and you feel there is a little pain, right? But if you raise the pen high up and you release it from that point, or maybe you ask your friend to stand and release it from a high point, as it hits you, it will be more painful. It's going to be more painful. So we want to determine why. We want to explain that. So here is the reason. This is because upon falling from a 10-meter height to the ground, the speed of the body increases. So it accelerates. As objects fall, they accelerate, they increase in speed, right? The gravitational force causes object to accelerate towards the center of Earth. The acceleration due to gravity is denoted g. Near the surface of Earth is taken as 10 meters per second squared. This is the value of the gravitational acceleration that we are going to be using in our calculations, right? Take an empty 500 milliliter plastic water bottle. Drop it first from any high and secondly from about shoulder high. What can you say about the sounds made as the buckles hit the ground from these two different heights? Okay, these demonstrations, you should carry them out. It will actually make you understand. Don't just take my word for it. Do this demonstration. You have to be sure that you understand what we are talking about here, right? If we ignore air resistance, all falling objects will experience an acceleration of 10 meters per second squared. So for all our calculations, we are not going to consider air resistance. If we do, we can't make any calculations, right? So now let's look at how the speed and acceleration changes as the object is thrown upwards or as it is dropped. Well guys, here is our first illustration. So in this case, this object is dropped from this height, right? It is dropped. So initially this point, the velocity is equal to 0 meters per second. It's 0 meters per second. Then after 1 second, the velocity is now 10 meters per second. After a further 1 second, the velocity is now 20 meters per second. After a further second, the velocity now is at 30 meters per second. So the total time taken here is 1, 2, 3. So from 0 to 30 meters per second in 3 seconds. This happens in 3 seconds when the object is dropped. And remember, we are ignoring air resistance. So there is no opposing force because air resistance opposes motion. What do we notice? From here to here, the speed changed by 10. Up to here is also 10 meters per second. From here to here, the speed changed by 10 meters per second. From 0 to 10, the difference is 10. From 10 to 20, the difference is 20. From 20 to 30, the difference is 10. So what can we say? The velocity is increasing by 10 meters per second every second. What we have just defined here is what? The acceleration. Therefore, acceleration is 10 meters per second squared. So acceleration for, let me change the color. Acceleration for free fall, A, is denoted with G and is 10 meters per second squared, is directed vertically downwards. So we want now to see how this graph will look like. We are going to look at the speed time graph and the velocity time graph. Under free fall, they are not always the same because the direction changes, and velocity gives us more information about the direction because velocity is a vector. Velocity is a vector quantity. It tells us the magnitude and the direction. Speed doesn't care about direction. So let's see what happens in this case. Well, here is a speed time graph, here is a velocity time graph. They are the same. Why are they the same? Because the direction is not changing. The direction is the same. So when the direction is the same, speed and velocity will be the same. The only difference is when now the direction changes. Like when you throw something vertically upwards, it goes up, then it comes back. In that case, the graphs won't be the same. And also we are saying, note, straight line shows that acceleration is constant. Straight line, what does it tell us? The slope is the same throughout. So the slope is not changing, acceleration is not changing. Therefore, it is constant. So now we want to look at illustration number 2. Well guys, here is our illustration number 2. In this case, the object changes direction. It's thrown vertically upwards, then it stops at the maximum height, then it comes down. Well, we start from this point. From here, the object is thrown vertically upwards. To throw something upwards, that means you should give it an initial velocity. If you don't do that, it won't move. It won't move, right? Yes, so let's choose the initial velocity. So we choose the velocity of 30 meters per second, right? After 1 second, the velocity will be, because when the object moves upwards, like we have seen in our illustration using the simulation, we demonstrated that the speed decreases as the object goes up, right? So here we have 20 meters per second. After 1 second further, the speed will be 10 meters per second. At this point, it will be 0 meters per second. After a further second, it will be 0. Now at 0, at the maximum height, the object is at rest. At maximum height, the object is at rest. When you throw something vertically upwards at maximum height, it is 0, right? So here we have 0 meters per second. Here, same point, it will be the same velocity, 10 meters per second. On its way up, at this point, the velocity was 20. Now the velocity is also 20 at the same point, but going down, 20 meters per second. Now, for this part here, this point, it was released at 30. It will arrive at that point at the same velocity, 30 meters per second. Total time of going up is the same. It's 3 seconds. 1, 2, 3. Provided the initial position is also the final position for the object being thrown upwards, right? So this is what happens. This happens because as it goes up, the acceleration is negative 10 meters per second. It's negative 10 on its way up. Let's write this. On its way up, g is equal to negative 10, right? G is equal to negative 10 meters per second. As it comes down, g is equal to positive 10 meters per second squared. Meters per second squared. So as it goes up, the speed is decreased by 10 meters per second every second. When it comes down, the speed is increased by 10 meters per second every second. So this is what happened for an object thrown vertically upwards. So now we will want to look at the graphs. How will the speed time and velocity time graphs differ? Well guys, here is our speed time graph. So what does it tell us? It tells us that from time is equal to 0, at the beginning, the object had a velocity of 30. Here is a velocity of 30. Then after 1 second, it was at 20. After 2 seconds, it was at 10. After 3 seconds, it was at 0. So this point is the maximum height reached by the ball. Then after that, the object increased its speed from 0 to 10 in 1 second, right? Then from 10, after 5 seconds, it was at 20. This is the 20. Then after a total of 6 seconds, it was at 30. This is 3 plus 3, making 6 seconds. And notice one thing, from this we cannot tell whether the object has changed direction or not. We might think maybe it was just reducing its speed, then coming to rest, then starting again, moving in the same direction. Speed time graph does not tell us the direction. Let's look at the velocity time graph. How do they differ? Well, here is our velocity time graph. Shown here is a velocity time graph. And one difference that needs to be noted here is the negative values. The negative values, there should be a negative value here. Negative 8, right? The negative values, what they tell us is the direction. The negative values are purely directional. If we have 30 meters per second and 30 meters per second, negative 30, that means these two speeds are of the same magnitude, but the direction, they are opposite. The directions are opposite. If the other one is going up, the other one is going down. If the other one is going to the right, the other one is going to the left. So that's what it means. Now let's look at, because from here to here they are the same. From here to here they are the same. Now when the direction changes, because this is at this point, the direction, the object was going up to this point. Yes, we see that it's shown here in one particular direction, and the values of the velocity are positive, all of them. After 3 seconds at this point, the velocity was 0. Velocity is 0 here. Now the direction changes. The object moves downwards. The object is going downwards, right? So what does this graph tell us? It tells us that the motion is now in the opposite direction, because we see these negative values. So that's the one fundamental difference between speed and velocity, direction, right? So this is how the graphs differ. Yes, for this one, it just goes for speed. Remember, it was just in the same direction in a way. It doesn't tell us the direction. These are positive values. So the speed cannot have negative values. Speed cannot have negative values. Distance cannot have negative values, because it's a vector. A vector does not have direction. If we include negative values in a speed time graph or distance time graph, then your distance becomes displacement. Your speed becomes velocity, right? So remember, speed is a vector, not direction. Negative sign means direction. As you can see here, the negative sign in the acceleration is purely directional, like it's going up. On its way down is now positive. Positive, we normally don't include the plus sign. There is no need, there is no confusion. Remember, the magnitude is the same. The only difference is the negative sign, which is purely directional. Okay, another thing that we need to maybe to emphasize is this. Well, here we are saying time taken going up is the same as time taken going down, right? We have proven that. Velocity at same point is the same for upwards and downwards motion. Another thing, at maximum height, the velocity is always 0. These are the things that you need to remember, because sometimes when solving questions, you might think you're not given enough information. But the fact that there is maximum height, the final velocity has to be 0. And also, when an object is dropped from a height, initial velocity is 0, because it's not thrown downwards, it is dropped, right? Those are the things that you should always highlight in your notebooks, so that when you are solving such questions, you know what you are expected to know.